Hello guys, welcome back to the channel. This is the second video in our networking fundamentals playlist. In the last one, we broke down the OSI model, and today we'll be delving into the TCP IP model step by step, but this time not just in theory. We are going to use a network analysis tool called Wireshark to capture real network packets and see exactly how each layer works in action. And by the time we are done, you'll be able to link classroom concepts to real-world networking. So without wasting much time, let's get in. So, what exactly is a TCP IP model? It is basically a framework that defines how data is transmitted between devices across networks, from the device all the way to its destination. Unlike the OSI model, which is more of a conceptual guide, the TCP IP model is the real-world standard that powers the internet today. It is a practical backbone of networking and is what every packet of data you send or receive actually follows. The TCP IP model consists of 4 layers. In ascending order, they are the network access layer, the internet layer, the transport layer, and the application layer. Sometimes you may see the internet layer being referred to as the network layer, and also the network access layer being split into 2 further layers, which are the physical layer and the data link layer. With that being said, let's begin where you and I actually interact with technology, the application layer. The application layer is not about the applications we use themselves, but it's about the protocols which these applications use to communicate over the network. Some of these protocols include the hypertext transfer protocol, the secure mail transfer protocol, the file transfer protocol, among others. These application layer protocols work by defining the rules for data exchange, ensuring the correct formatting of data, and also establishing and closing of sessions, which could be logging into a website or starting a file transfer. So by way of demonstration, we are going to capture some HTTP traffic and then we see how HTTP works in action. So I have this local web file here, which we are going to input our username and password for authentication. But as you can see from the URL, there is a local file, so it is safe to use for testing purposes. So my password is just going to be password. Then as I click login, we'll go into Wireshark. Then we are going to apply HTTP display filter to filter out only HTTP request. We take the first packet, which is the post, and then so we can see from the hypertext transfer protocol section, the request method is post, which is indicating that we are submitting data to the server. If it is get, it means we are retrieving something from the server. We can see the request version, you can see the host site we are communicating with. This is important because the server can host so many sites, so it tells us which site we are communicating with on the server. We also have connection, which is keep alive, which indicates that our connection is still alive because there's communication ongoing. And then we come down, we have user agent, which says we are running Mozilla Firefox on a Windows machine. We also have accept encoding, which tells the server we can accept compressed data. And then we have accept language, which says we can accept US English and any other English. So we come down also to the form item, and then we see our username and password is being transferred in plain text, and this is because it is just HTTP. So we can see our username is test user and password is just password. So if you want to see an encrypted communication, I have this web page open here, which I'm going to reload in a bit, and then go back to Wireshark and apply a display filter TLS. So now we have an encrypted communication process going on, so we can take any data packet from here, and then we come down to the transport layer security section, and then we can see here encrypted application data. So unlike the HTTP, which we saw everything in plain text, this is now encrypted, and this is the long ciphertext of whatever message we are sending. So that is a brief of how HTTP request works. After application layer protocols have formed the data, it is the transport layer that does the transportation of the data. It ensures data gets to the right application on the host and manages the quality of that delivery. 2 of the main protocols being used here is the transmission control protocol and the user datagram protocol. TCP uses a mechanism called a 3-way handshake to establish a connection between the client and the server before the data transfer takes place. In the first step of the handshake, the client sends a SYM packet to the server with a sequence number set at any random number, which can be say 100. If the server now replies with a 2-in-1 message, which acknowledges the client's sequence number, adds 1 to that, which is going to be 101, and then adds its own sequence number, which can be say 500. In the third and final part of the handshake, the client adds 1 to the sequence number of the server and sends it back to it as an acknowledgement packet. So the whole process of the three-way handshake is more like calling someone on a mobile phone and saying, "Hello, I want to talk to you." The person replies, "Hello, I'm also listening." And then you tell the person the third time, "The network is okay, we can now talk." Now, with a connection being established, TCP uses port numbers, which identify services running on networks, to deliver data to the right application on the communicating devices. Sequence and acknowledgement numbers are also used to ensure data is received in the right order, which helps in the retransmission of lost packets. It also uses a sliding window to control the flow of data between the client and the server, to ensure that the client is not overwhelmed with so much data than it can accept. During the transmission of data in the TCP setup, a timer is sent to every data segment sent, and an ACK packet is sent back from the client to the server for every data packet it receives. This is crucial for ensuring the reliability of TCP, as the lost packet is retransmitted as soon as the timer is up, and then with the help of the sequence numbers, data segments are now rearranged in the right order. Now, in the case of the user datagram protocol, the UDP, there is no initial connection being established, there is no retransmission of data, it's just the port numbers being used to send and receive the data segments as they come. This makes it a very fast and efficient transfer protocol, and it is best used for live streaming purposes, voice over IP calls, online gaming, and video streaming purposes. When missing a few data segments is not going to cause the whole data communication process to just collapse, but just a minor glitch is going to occur, and then we get back to the data transmission. So here we have Wireshark open, and then we have a packet being selected here. So we'll go down to the transmission control protocol section. We drop down this list, and we can see we have source ports, which is a random port the application chooses for its communication processes. We have the destination port 443, which is used for HTTPS. And then we come down to the sequence number, which is 1. And then we see this is a relative sequence number. We have the raw version. This raw number is a number which we cannot start counting from. It's a very big number. So Wireshark gives us a relative version of it, which in this case is 1. Very useful. And then we have also the relative acknowledgement number. Then we have the flags, very important. This has the PSH, which stands for the push flag, and the ACK, there's acknowledgement flag. The push tells the operating system to push this data packet right to the application. There's no need for buffering or anything. This is more like an agent stamp on the data packet sent to the application right away. And this is an ACK flag, which is telling the server that you receive your previous packet. And then we have the window size, which shows the server how much data we are willing to receive to prevent overloads. And then we come down here, and you can also see we have the TCP payload. So since this is a communication on port 443, which is for HTTPS communications, this TCP payload is probably encrypted, because HTTPS, as we know it, encrypts data in transit. Having seen how the transport layer handles communication process or data transmission between applications, it's time to look at the internet layer, which handles the transmission of data between networks. The main role of this layer is to get data packets from the original source to its final destination, irrespective of where they are on the map. This layer is almost the heart of the entire TCP IP model. Its most important jobs are logical addressing, which is basically giving every device a unique IP address, and then routing, which is determining the best path for the packets to travel across other networks, and also packet forwarding, which encapsulates the TCP segments into IP packets and then sends them to the best paths it has determined for them to travel across to get to the destination. An IP packet is the protocol data unit of this layer, and it contains all the crucial information for the delivery of the packet. It contains information like the source IP address, which is the logical address of the sending device, and then the destination IP address, which is the logical address of the receiving device, and this never changes throughout the routing journey. It also contains a TTL, which is an abbreviation for time to live, and it's a counter that decreases at each hop or router in the packet forwarding process. And as soon as it hits 0, the packet is then discarded. This prevents packets from being stuck in a loop on the internet. It also contains an important field called the protocol, which identifies the transport layer protocol inside the IP packet. This is how the destination device knows whether to give the payload to TCP or UDP. Devices called routers operate at this layer. They have what we call routing tables, which are basically maps of the network that tell them the best path to send a data packet to, so it gets to its final destination. Data packets rarely go directly from source to destination. Each router only knows how to get it to the next hub, which is the next router on the path. This process will repeat itself until the packet reaches the network of its final destination device. And that is why the IP address of the receiving device doesn't change in the whole process, because once it changes, another device is going to receive that IP packet. So we are first going to open command prompt, and then first I check my IP details, IP config. So you can see from here that my IP address is 172.20.10 and then .7. So I'm going to pin my default gateway. So we run a simple pin command to 172.20.10.1. Then as we hit enter, this is going to basically what a ping command does is just check if this device is online, check the availability of the device. So we are going to filter out ICMP request, which is the Internet Control Message Protocol. This is the protocol ping commands use. So we are going to filter out this protocol, and then we take this request, which is the first one, which is from the source we can see from my IP address to the router, the destination IP address. So we come down to the internet protocol layer, the IP layer, and then we can see right away some information about the packet. The source is from this device 172.20.7, and then the destination is to .1, which is the gateway. And then we also have the version, which tells us this is IPv4. We have the header length, which is mostly 20 bytes. We have the time to live here, which tells us that this packet can travel through 128 hubs before being dropped, but it doesn't necessarily have to go through 128 hubs. That is what this is. And as you can see, this is the protocol here, ICMP. So if this was a UDP or TCP, we are going to see TCP here, and the number will be 6. If it is UDP, it is going to be UDP, and then the number associated to UDP is 17. And then we can also see important again, the source address and then the destination address. So basically, that is what an IP header contains. At this point, the application layer has crafted the data. The transport layer, with the help of TCP, has segmented the data and ensured it has gotten to us reliably and in order just as it's left. And the internet layer has made it possible for the data to reach us from wherever it's coming from across the globe. But it has still not gotten to our device yet. So it is now the role of the network access layer to make sure that the data actually gets to our device, which is within the local area network. It is responsible for the physical delivery of data over the network medium. Its main functions include framing of data packets, physical addressing, and also error detection. MAC addresses are unique 48-bit hardware identifiers that allow devices to be distinguished within a local area network. The data being passed down to this layer is an IP packet, but this layer doesn't deal with logical addressing. So it also goes through a process called framing, which is the encapsulation of data by adding headers and trailers with addressing information such as MAC addresses, ensuring that the data is delivered to the correct device within the local area network. It also performs a crucial function in error detection, which helps maintain the integrity of data by using frame check sequence. Before transmission, the sending device performs a cyclic redundancy check calculation on the entire frame, which is the header and the payload together. The result of this calculation is placed in the FCS field and appended to the trailer of the frame. On the receiving end, the receiver performs the exact same CRC calculation on the received frame and then compares its results to the FCS value sent in the frame. If they match, the frame is considered error-free. The frame header and trailer are stripped off and the payload, which is the IP packet, is passed up to the internet layer. If they don't, the frame is silently discarded, it is not acknowledged, and no request for retransmission is sent at this layer. Retransmission, as we've discussed, is done by the Transmission Control Protocol. This shows the interoperability of the TCP IP model. Another important protocol being used in this layer is the Address Resolution Protocol. This protocol serves a very important purpose in mapping MAC addresses, which are the physical addresses, to the IP addresses, because as we've learned, the internet layer deals with the destination IP address of the device, not its MAC address. So this protocol comes in and then maps the IP address to the corresponding MAC address of the device and making sure that the data actually gets to that device. Some devices that operate at this layer includes the network interface card, which is the physical hardware that connects a device to a network. It has a unique burn-in MAC address and handles frame creation, CRC calculation, and media access. A switch also works at this layer, and what a switch basically does is it learns which MAC addresses are on which ports by examining the source MAC address of the incoming frame. It then forwards the frame intelligently only to the port where the destination MAC address is located. So here we are again on Wireshark, and now we are going to look at what the Ethernet frame looks like. So just pause the capture here, and then we take one packet, then we go down to the Ethernet section, then we are going to drop down the list. So from here we see we have the destination MAC address of the device to receive the data, and we have the source of the device sending the data. Then we also see here we have type, which is very important, which tells which type of protocol to give this to at the internet level. So if this is IPv4, it is telling us that we are giving this to IPv4 processes at the internet level. So bringing it all together, we've seen how application layer protocols like HTTP or crypto requests pass it down to the transport layer, and depending on the protocol being used, either TCP or UDP, a header is attached to it. It also passes it down to the internet layer, where an IP header including a source and a destination IP address is also attached to it. Also pass it down to the network access layer, which also adds a frame header, which here includes a source and a destination MAC address. It also adds the FCS value to the trailer, which is used for error detection. And then finally, data is transmitted in this layer over physical mediums, be it light waves, radio waves, or physical electric cables. I hope this video gave you a clear understanding of the TCP IP model. In subsequent videos, we are going to explore the most commonly used protocols at each layer of the model. Don't forget to like, share, and subscribe to the channel so you don't miss the upcoming videos. Thanks for watching.